Hi everyone, my name is Iman Taraki. I'm a PhD candidate at Sheffield Hallam University, and today I'm going to present to you a sleep-inspired solution that aims to enhance learning for teachable robot. So first, why are we interested in teachable robot? Well, with the significant advancement that we've seen in robotics in the last decade, this progress led to elevate as well the expectation of the end users. What they want now is to have robot that they can personalize the behavior, of the robot to the specific task and goal they have in mind, without necessarily having the skills, the technical skills to do it. So without coding the robot or anything, just by teaching it. So one way to achieve that is through human feedback reinforcement learning. So in this setting, you have a user that will observe the robot takes different actions. The users will then provide feedback to the robot that the robot will use to update its policy until it learns a behavior that converges and is aligned with the intent of the users. Specifically in this work, we focus on evaluative feedback. So the users will give feedback that assess the correctness of the action by either saying if that was a good action, a bad action, or just saying neutral, not saying anything. So for human feedback reinforcement learning, we use reinforcement learning for that. And one key aspect of reinforcement learning is the reward function. So that the aim of an agent in reinforcement learning is to maximize the overall reward it can get. And one key factors that tells about the sensibility of the robot to the future action is the discount factor. So discount factor gamma closer to 0 means that the robot will only care about the immediate reward it can get from the next action. A discount factor gamma closer to 1 means that the robot, when taking an action, will consider the long-term consequence of that action on the reward it can get from all the episodes. In classic reinforcement learning, we usually use a discount factor closer to 1. However, this doesn't always work with humans, because when you learn from human feedback, well, you observe that humans have a positivity bias. So what they will do is that they will try to give more positive feedback to the robot rather than negative ones. And this can lead to positive cycles. So what is a positive cycle? Well, with a normal setting of reinforcement learning, meaning that the discount factor is closer to 1, the robot will try to exploit this positivity bias of the human. For example, if you consider this environment, when the robot starts in this position, has to go all the way to the red flag without stepping on the grass, the robot knows that by going up, then right, it will get positive feedback. But he also knows that by being in that particular state, that if he goes down, then left, then up, and right, he will still get positive feedback. And the aim of reinforcement learning is to maximize the number of feedback and reward you can get. So what will happen in this case is that the robot will try to revisit the same step again and again in order to maximize the number of positive feedback it can get. This will create positive cycles, and it's not aligned with what the human wanted to learn, because the human wants the robot to go to the red flag rather than just repeatedly visiting the same state. So studies have found that if you use a discount factor closer to 0, that will create myopic learning, because the robot will only care about the immediate action, and that will break the positive cycle. So for example, in this state, the robot knows that going down will not lead to any positive feedback, but while going to the flag will give him a positive feedback. So he will not care about the consequence of going through the reward that it can get in the other state, but will only care about the immediate reward, which is going to the flag, and which will allow the robot to learn from human feedback. And myopic learning is good because it accelerates learning from the human, because the robot only care about the immediate reward. So it will spend less time exploring the environment to see which kind of reward it can maximize. So this allows us to converge more quickly to the optimal behavior, and also allow the human to have less load on him, because the robot will require less feedback from the human if the learning is quick. But the problem with less exploration is that it also means that the policy learn is less robust to changes in the environment, which is a problem, especially if we consider the real-time deployment of robots, because our environment in real life are dynamic and they have changes. For example, if you take the same environment where the robot was able to run myopically from the human, and you just put an obstacle, the robot does no longer know what to do, because he did not explore the idea of getting to the right or other state. He was just like learning the optimal set of actions without really understanding why it was doing it. So the policy will not be able to generalize to that. However, as humans do learn from human feedback, and we do it all the time since we were babies. And a lot of developmental processes allows us to have this generalizable learning. And one key aspect of it is sleeping. So what do we do when we sleep? Well, we actually consolidate all the memories that we've seen through the days that are initially stored in the short-term memory, and we replay them while sleeping. And when we replay them, we actually straighten neural links that are associated with the memory and learning. And this allows to extract more generalized knowledge from the short-term memory into long-term memory that help us consolidate the learning that we've seen through the days. So what we want to do is to have a framework that is inspired by sleep that allows robots to learn from human to extract high-level knowledge from the human feedback. So we present the inverse forward of time reinforcement model that we call INFORM, and the model essentially consists of two phases. So in the first phase, the robot learns interact with the environment, and at each state and action, the robot will receive feedback from the human. The robot will learn myopically, as we've seen before, and he will use the feedback to update its policy until it learns a policy that is aligned with the human's intent. While learning, he will also store all the trajectories of the interaction in the environment in a replay buffer. In this case, a replay buffer will simply act as a short-term memory for the robot. For this, we use the established timer algorithms that have been tested with real-time users and have seen successful results of learning from human feedback. Then, after learning an optimal policy with the human feedback in a myopic way, we try to consolidate that learning by taking inspiration from sleep. So how do we mimic the sleeping pattern? So what we do is that we take all the short-term memories, the trajectories that we have stored initially in the replay buffer, and apply to them inverse reinforcement learning. So from inverse reinforcement learning, you have a set of trajectories and try to get a higher level, a policy that try to englobe these trajectories. And what this time we do it with a discount factor closer to 1, meaning that this inverse reinforcement learning will also care about the long-term consequence of the robot's action. So it will enable the robot to have a higher level knowledge of the bigger image of the goal of the task. But what we also do is that we try to recover a reward function that will act as an internal motivation for the robot to so that he can use to learn on his own without necessarily having a human teaching him all the time the same task. And for that, we use IQLearn, which is an imitation algorithms, but we slightly change it because in normal setting of imitation learning, we usually have expert demonstration given that are optimal. While in this case, the replay buffer doesn't have always optimal trajectories, because when we learn, we have successful trajectories, but also we have unsuccessful. And here it's important to consider what, because the successful trajectories allow the robot to learn a behavior that is aligned with the human. But the unsuccessful trajectory also allowed the robot to understand the dynamics of the environment, which allows him to also get a policy that would be more robust to changes to environment. So what we want to see is that how can INFORM learn a high-level policy just by replaying all experience. We want to see if the high-level policy is robust to changes in the environment, and we want to see if the reward function that we recover with INFORM does align with the behavior intended by the human. So for that, we consider 3 environments. One discrete grid where the robot starts in the S cell and has to go all the way to the G cell with the less number of steps and without bumping into any obstacle. And we consider a more complex and continuous environment, in this case, the pusher from Mujoko environment, where the robot has to put its ending factor on the cylinder and push it to the target area. For bar environment, we do not use real-time feedback, but just we simulate human feedback, because the aim is not to validate learning from human feedback. We just establish algorithm for that, but rather we're more interested into consolidating the learning from the human feedback. So that's why we're using Oracle to simulate it. So what did we find? So we trained both Tamer on the grid word and push environment. So Tamer learns a myopic policy from the simulated feedback, and we can see it does quickly converge to the expert performance for what environment. And then by taking all the trajectories that we stored from Tamer, we apply inverse reinforcement learning and recover the orange line, which is the performance obtained with the INFORM. In this way, with the discount factor, the gamma closer to 1. And if you can see in grid world, well, maybe you cannot see it, that because the INFORM performance matches from the first iteration the expert performance, so it quickly recovers, like from the first iteration, it recovers the optimal policy. And same for pusher, well, not that quick because the environment is more complex, but it quickly recover and converge to a policy that matches the expert performance without even interacting with our environment, just by replaying the memories. So we can see that Inform can learn a non-myopic policy from human feedback in an offline setting without further interaction with the environment. Now what we want to see is that how this high-level policy that we obtain with Inform is robust or not to changes in the environment. For this, we consider the push environment that we slightly change by adding an obstacle along the optimal way. So what we do is that we train both Timer and Inform on the original dynamics, and then evaluate the policies that we obtain on the pursuit dynamics one. So here's some example of the policies that we obtain. So for Timer, for example, in the evaluation, the robot only learned how to do the set of action, is just pushing the object from here to here without understanding what was the goal. So when he encountered the obstacle, the cylinder just go away, but the robot doesn't know that he has to position again its end effector on the cylinder, so he cannot know. He just keep doing the same movement. But for Inform, the robot understood the aim of the task, so he just crossed the cylinder, go around the obstacle, sorry, and put it to the targeted area, and that's what we want. So just to quantify this result, like for example in here, we calculated the distance between the end position of the cylinder and the targeted position that we want the cylinder to be. And we see that for Inform, for example, it's significantly go closer to the targeted position. And and this was done for 3 different agents on 100 episodes each. So we obtained this result for many agents, and we can see also for the trajectories, like for one agent on the 100 evaluation. You can see for original dynamics that both Timer and Inform learn to go to the optimal to the goal position, while for me introduced the obstacle, Timer had a hard time going because the cylinder was just pushed away and the robot could not even find it to go back, while for Inform, the robot significantly go around the obstacle and put it in the position that we wanted. So we can see that Inform, by learning a non-myopic policy, so we hope that obtain a higher level environment, a higher level knowledge from the environment, was able to learn a policy that was more robust to changes in the environment. Now we want to see how the reward function that we recovered from Inform, if it's recovered the goal of the task or not. So what we did is that we went back to the reward environment, we trained and Inform on it and recovered a reward function. Then we consider this environment where we added an obstacle. Well, we did so because we want to see if the reward function understands the goal of the task, which is go into the G cell without bumping into walls in the shortest way possible. So if we kept the same environment, we know if the reward function understood the goal or it just mimicking the behavior of the optimal policy. So we changed it just to see that. So what we did is that we considered 2 agents, one learning with the reward that we recovered from Inform, and one learning from another learning from the environment reward. In the environment reward, we just said like the robot will have received 0 feedback and a +1 when achieving the goal. So the goal was to is to go to the cell the more quickly possible. So this is the learning curves that we got, and we can see that for Inform, the orange line, the robot converged to the expert policy with the dashed green lines more quickly even than with the environment reward. So not only that the reward function that we recovered with Inform understood the task and allowed the robot to go to match the performance of the expert and understood that it has to go to the goal, but also it did it in a more quick way than with the environment reward that we coded. What happened is that because what we found is that the Inform reward that we recover is denser, so it gives more information about each state, which allowed the robot to converge more quickly to the optimal behavior. So this is just an evaluation just to compare between Timer and Inform. Just to be fair, Timer was not trained on this environment. We just tested the evaluated policy obtained and the original dynamics, because just here to highlight that with the reward function, Inform was able to learn on his own and adapt to the new environment, while Timer, without any reward function, without just a myopic policy, just understand the sequence of options. So here he knows that he needs to go up, but he cannot adapt to it. He would need another human to teach it this the new behavior on this new task, while Inform with the reward function that he recovered was able to run on his own. So we can see that Inform can recover a reward function that is aligned with the goal of the task, but also it allows autonomous learning for the robot so he can learn on his own with reducing the human load. So just a few limitations of this work, we use simulated feedback. So while it was good to validate the initial architecture, it would be interesting to evaluate this in real time with users as well. Also, we considered feedback. The simulated feedback were all rational, so we had perfect and accurate feedback all the time, which is not true with humans, because humans can give inaccurate feedback sometimes. We want to see how this irrationality can impact the performance of Inform. But also, we need to quantify the number, like the quantity of data that we need to have good performance, because in here we had access to unlimited training because it was simulation. But in real life, the human will not be able to train robot much longer. So maybe the short-term memory will have less trajectory solved, which might impact Inform. So that's studies that we're considering for future works. And just to sum it up before closing this presentation, we presented Inform, which is a sleep-inspired framework that aims to first learn a myopic policy from human feedback, then use a sleep-inspired inverse reinforcement learning in an offline setting to learn to consolidate that learning. So we saw that Inform can recover a high-level policy, non-myopic in an offline setting from human feedback. We saw that this policy is robust against changes in the environment. And we also saw that the reward function that we retrieved was able to recover the goal of the task, but also allows the robot to learn autonomously without any human teaching it. So thank you for your attention. Here's the paper website for more details. And if you have any question or feedback, please email me. Thank you.